Hi, my name is Brian Edwards, and I'm going to talk to you a little bit about our recent work in New Journal of Physics. The electric tweezers are a touchless manipulation technique based on dielectrophoresis and electroorientation. The goal of the work is to provide an economic alternative to optical tweezers that can be easily added to any microscope. Since our first experimental publication on this work, we have made several major advances, which we will describe here. At its heart, the electric tweezers consist of an array of fixed electrodes. These can be fabricated onto a microscope slide out of gold using simple lithographic techniques. This forms a small arena in which we can manipulate one or more particles. The electric tweezers operates by calculating and applying the correct voltage to each electrode to generate the arbitrary force and orientation you want on each particle, simultaneously and in real time. For instance, suppose we have two particles, each with a desired force indicated by F and an orientation indicated by E. We'll model these particles as induced dipoles, and as such, they will naturally align with the electric field. If their polarizabilities are negative, and this is often the case for biological cells, they will tend towards regions of lower electric field intensity. The electric tweezers find the least strenuous voltage set that satisfy these constraints. Plotting the resulting voltage field with the dipole potential, we find that these voltages have generated an electric field in the correct directions, and that these negatively polarized particles will indeed float towards regions of less field in the desired direction. The ability to create arbitrary motion is what separates the electric tweezers from other dielectrophoretic work. Here, we tell the particle where to go, and we are free to change our mind at any point. The motion is arbitrary and reversible. We created custom electronic hardware to generate the voltages because it simply did not commercially exist. This bank of 16 synchronous, real-time programmable bipolar square wave generators fits on a single PCB board. The circuitry and microscope slide electrode array can be placed onto an upright or inverted microscope stage. The software, which manages user input, monitors the particles, and calculates the voltages, resides on a laptop. On the left, it shows the voltages sent to each electrode. In the main field, it shows the real-time image from the camera. The large circle shows where the software has identified the particle to be and the electric field direction prescribed at that point, while the small circle shows the particle's set position. When the electric tweezers are engaged, all the particles immediately respond, and the two negatively polarized glass beads are herded back to their set positions. However, the particles that we're not controlling drift towards the field minimum, which typically exists near the center of the array. In our previous work, we manipulated a single positively polarized gold nanorod. In this paper, we show that we can manipulate two negatively polarized particles at the same time. Since the force is calculated based on the polarizability, the electric tweezers could easily manipulate both positively and negatively polarized particles together. However, the electric tweezers has little effect on particles with small polarizability. This could be advantageous if we have many particles that we wish to manipulate serially. We see a small piece of debris on the microscope slide that has only a weak negative polarizability. Here we demonstrate how we can use a cluster of glass beads to apply mechanical forces to it and move it around without direct control. The details of this work are of course in the paper, but I hope you found this little taste enjoyable. Thank you.